Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. In today's topic, we will see staggered, collocated, and semi-grids actually. So, what are the significance of the staggered grid, and what is the significance of the collocated and semi-staggered grid? We'll see. So, these topics will give us knowledge about how do we store the variables in the grid arrangement. So basically, we have seen what is grid actually. So and what are the grid points and what are the center of the cells. So these aspects we have seen. Now, so we are also seen the different types of CFD techniques which are used for running the CFD simulations. So those grid techniques when we run, so they have to be stored at certain locations. So let's say we have pressure as the variable, density as a variable, temperature as a variable, velocity as a variable. So these variables, where do we store actually? That is very very important. And how do we store and how do we access them? Those things are required for CFD analysis. So before that, let's actually recap what are the CFD techniques which are available and what are the algorithms that we have discussed. We will have a small recap and then we will get to know why we need that type of arrangement. Okay, so we have seen the simple algorithm. So where we have performed this algorithm using the guess value of pressure. So this value will be going and solving for the momentum equation to get the output of V star. Once we get this output, so we will use the pressure correction equation to get the exact value of V with respect to V star, this one. Then, so whatever the velocity we get, so we'll substitute in the continuity equation, and then we will be using them to solve the temperature, turbulent kinetic energy, internal energy equations, and we'll check the residue whether it is converged or not. So once it is converged, we will stop it. If it is not converged, then we will perform the loop again with the output of the first iteration. So let's say we have output of the first iteration, P is let's say 0.9 atmosphere. So that will be the new guess value for the second iteration. Okay, so this is what we have simple algorithm. Next, we have simpler algorithm. So here what we do, so same, the initial guess values will be P dash, P star, U star and V star. So these values will go for the discretized momentum equation. So already we have seen what is discretized momentum equation. So that will be U of I to the power of n plus 1 minus U of I to the power of n divided by delta t plus C into, so U of I plus 1 to the power of n minus U of I to the power of n divided by delta x equal to 0. So this is what we have the discretized equation. So in this discretized equation, we will substitute the values of P star, U star and V star. Okay. So once we substitute them and then we'll get the required output of U star and V star, then we will use them to solve the pressure correction equation. So in the pressure correction equation, we will get the value of P dash. So the actual P is equal to P star guess value plus P dash. So the correction equation. Next, actual velocity U is equal to U star plus U dash we have. Okay. So this is what we have. Fine. Then we will use the actual velocities and pressure what we obtain in the continuity equation. So what is continuity equation? We have dou u by dou x plus dou v by dou y equal to 0. This is for 2D incompressible flow. Okay, here we'll substitute and we'll see whether it is perfectly becoming equal to 0 or there are some residues. So here this is the PD equation which I have written. So when we write in discretized form equation, so this will be u of I comma j I plus 1 comma j minus u of I comma j divided by delta x plus v of I comma j plus 1 minus v of I comma j divided by delta y equal to 0. So this is a discretized equation of continuity. So here we'll substitute these actual values and we will get what is the exact value when we substitute. So let's say it will not be equal to 0 as I told you. So when we are doing the finite difference discretization, so there would be some residue actually. Residue in the sense the error of the higher order terms which we neglect during Taylor series of expansion. So the residue, it will come initially, let's say 1e minus 2, 1e minus 4, like it will keep on decreasing if the simulation is correct. So once it is done, we will set a convergence criteria where this has to meet 1e minus 8, let's say. So you will check the simulation iteration process such that so the residue reaches 1e minus 8. Once it reaches, then you will stop it. If does not reach, so again you will use this end result with the initial values. Okay, so this is like a iterative process where so initially you will store the values and then you will override the values with respect to different aspects. Okay, so that is simpler. So here simpler algorithm. So we have seen simplex is the adaptation from the simpler. Here, instead of going directly to the initial guess values to the discretized momentum equation, so here we use other term called pseudo velocities or like pseudo variables, where we will solve additional momentum equation using the guess values and whatever the output we get. So we will name it as u cap, v cap, and let's say p cap. So these u cap, v cap, and p cap will be used to solve the discretized momentum equation. So from that you'll get an output to solve the pressure correction equation. So the difference what we observe is additionally we will solve one more equation before we substitute directly the initial guess values in discretized momentum equation. So that is the pseudo correction. So which is additionally we will solve momentum equation. Then once we do it, the similar procedure what we have obtained is the same. So this simplex. So these are steady state solvers. So steady state solvers in the sense the time derivative terms, dou u by dou t terms, they are negligible. So we don't have those terms in the equations what we used to solve the algorithms. Okay, so this is basically called the steady state solvers. We have one more which is called piezo, which is called transient solver. So here dou u by dou t terms you cannot neglect. So this should be present. So these terms are very important. So these should be present, and in order like after starting the simulation, so we will initialize the time step. So initialization in the sense at t is equal to 0, so what is the value of p, what is the value of rho, what is the value of t, what is the value of u velocity, v velocity. So these aspects we have to initialize. After that, so then we will take time step, let's say delta t of 0.02 seconds. So at every 0.002 seconds, so the simulation, whatever the data it is giving output, it will be stored. So let's say initially the stored data we are located at locations P1, rho 1, T1, Q1, say V1. Okay, so these values. So next that will be P2, V2, T2, and V2. So these will be the second. So in the same way, whatever the time steps you have, let's say you have 100 seconds till 100 P100. So those things will be stored. Okay. So it why, because we need to see the residue products. You have the plot. This is time and let's say this is velocity. So it is starting and it is fluctuating like this, and somewhere it will get steady state. So how much time does it take to settle down the value of velocity? It's not about only velocity, it's about pressure, temperature, and density. So all the flow variables initially when you're starting the simulation, they tend to oscillate in the sense they will have some time required to settle down the exact values. Why? Because so whatever the value we are calculating from the boundary points to the internal point. So during the calculation procedure and during the algorithm solving, so we have to see the residue contours also. So these oscillations are because of the unconverged portion of the simulation. So where the error still represents this oscillation. Once the error is decreased and once the simulation is approaching the convergence, then you have these steady state solutions. Okay. So here in the piezo algorithm, which is used for the transient solver or the unsteady simulations, so we will actually start with the initialization variables. Then we have to initialize the time step. Then here you can see we will solve momentum equation explicitly two times. One, and here you have two. So yeah, we have velocity correction. Sorry, not momentum. Velocity correction one, velocity correction two. So two times. So once we solve the momentum equation, we need to solve the velocity correction twice, and then you have pressure correction twice. And this algorithm what I have shown is for the compressible flow. Fine. So this is how the algorithms are solved for the different stages. Like let's say a simple algorithm, simplex, which is for steady state solvers. So piezo, which is for transient solvers. Now the thing is, so where do you store? So to solve these things, actually, first where do you store, and how do you access the variables is very important. So for this, we are seeing the grid arrangement. So here, first we are calling like staggered grid. Staggered grid in the sense. So here you can see a square domain. So this one we say this wall. Okay. So here, whatever the points we locate, so these points, so we say it as boundary points. Okay. So the other points, what we have is grid points or internal points. Okay. So here you can see that the pressure is stored at the centroid of the cell. Okay. So the pressure is stored at the centroid of the cell, density is stored at the centroid of the cell, and the scalar values are stored at the centroid of the cell. So what is the meaning actually? When the simulation is started, or let's say before started, so what happens? The value of flow variables are stored at the centroid of the cells. So here, okay. So once the simulation starts, so what happens at each and every time step? So these values will get updated. So let's say this is 1, this is 2, this is 3. So at T1, so these values will be initially P1, let's say U1, V1, T1. So at T2, so the value will get overrated and it will be stored at these locations. Okay. Or you can save the data set at each and every iteration. Okay. There is no problem with the storing of data set at each and every iteration. Or let's say you want the final result or the updated result. So then you can skip saving the data step at each and every time step, and you can get the value or the variables at the, let's say we are solving till 100 seconds, t 100 seconds we will get the values. Okay. So here in the staggered grid arrangement what we have, so we are storing the values of flow variables at the center of the cells. Okay. Let's say the scalar variables, and other, so we have velocities. So what velocity? U velocity and V velocity. So you have U velocity in this direction, V velocity at the cell faces. Okay, so you can see this is the momentum cell, and you can see this is the continuity cell, and this is solid boundary. Okay, so this is what we have for the staggered grid arrangement. So the variables density, pressure, velocity, they are not stored at the same location. They are stored at the different locations. So at the center of the cell, the scalar values are stored, and at other faces, so let's say you have boundary faces. This is phase 1, 2, 3, 4. Along y faces, you can see that the x values are stored. Along x faces, you see y values are stored. So that is what we have. Okay. So this is the difference. Next, we have one more grid arrangement called collocated grid arrangement. So in the collocated grid arrangement, so all the variables are stored at the same location. Same location in the sense here you will store the pressure, density, velocity, temperature. So all the values, all the variables at the center of the cell. Okay. So in the staggered grid arrangement, what do we have? So they are stored at the different locations. Scalar values are stored at the center of the cell, and the vectors they are at the cell faces. But collocated grid, what we have? So we have all the flow variables. All the variables are stored at the same location. So that is the difference. Okay. Now we have one more grid arrangement which is called semi-staggered. So semi-staggered in this is what? So some variables they are stored at the center of the cell. The other variables they are stored at the grid points. Okay. So you can see, so these grid points, here you have u velocity, here you have v velocity. Okay. So here we have scalars. Fine. So the semi-staggered grid arrangement is basically the combination, or you can say the collocated and staggered grid arrangement combination, you can assume. But the difference what we have is at the center of the cell you have scalar variables which is equivalent to staggered, but here instead of cell faces they are located at the grid points. Okay, here the center of the cell, here at the grid point. If we compare all the three, so you can see the comparison of all the three, where for the staggered arrangement, so what we have, so the scalar variables are stored at the center of the cell, and vectors are stored at the faces. Now in the collocated, all the variables are stored at the center of the cell. Now in the semi-staggered, so the scalars are stored at the center of the cell, and other vectors they are stored at the grid points. So basically the intersection of x lines and y lines, we get this grid point. So these are grid points. So these are what grid points. So at the grid points, we store the vector values. So here for the staggered and collocated, we did not store any values at the grid points. Okay. So this is all about the arrangement of flow variables in the mesh or the grid. Now, so what happens when the simulation starts? When the simulation is started, let's say from t is equal to 0 seconds or 1 second or 2 seconds, so the initialization happens where the initial values of pressure, temperature, density, velocity, so they are stored at these appropriate locations. So there are two possibilities. One, you can store the values of pressure, temperature, density, velocity at each and time interval t1, t2, t3, and you can compare them, or you can override them and get the final result. Okay, so this is what we have at different types of grid arrangement. Okay, so in the next session, so we will see, so what are the advantages and disadvantages of this grid arrangement, and then what are the corrections are required for this grid arrangement. Do we have any oscillation if we store all the values at the same point, or let's say if we have stored at the different point, what happens? And then if the oscillation happens if we store at the same location, how much memory is required. So these aspects we have to see in detail. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.